Hi, my name is Pierce Flood, and today I'm going to talk about engine cylinder configurations and balance, and how these impact various aspects of the engine, such as power. So before talking about the implications about these different types of engine configurations, we first need to establish what the different types of engines are, what the configurations are, and what they look like. So first, we have the boxer engine or flat 4 engine, which you see here. And so with this one, it's named a boxer engine because the motion of the cylinders essentially looks like a boxer punching, and the pistons here move along the horizontal plane. The next type of cylinder configuration we have is the V-shaped engine. And so it's V-shaped because the cylinders on either side essentially form the shape of a V, as like you can see here, and the cylinders on either side, they move at an angle away from each other. And so there are also W-shaped engines, but these are merely two V engines put together, and so for the purposes of this discussion, I'll just talk about the V-shaped engines because the properties associated with them are essentially the same. And then lastly, we have these straight setup engines, and where the cylinders are essentially lined up and move up and down along the vertical axis, like so. So one important aspect when analyzing various engine and cylinder configurations is that a balance has to be maintained, and each engine configuration has to achieve this. And so engine balance is crucial to the engine, or else the pistons can misfire and create unnecessary disturbance. And so rooted in achieving this is that there has to be a net force of 0 among the movements of the cylinders, and this is due to 3 explicit forces. So the first force is rotational force, and this is due to the rotation of the mass that is offset from the main bearing center line, which is the mass and the counterweight essentially right here. And so this rotational force has to be balanced throughout the different cylinders in order to maintain engine balance. The second force we have is the reciprocating force. This force is the up and down force that the piston experiences due to the continual acceleration and deceleration of each piston assembly. And so the reciprocating forces will be side to side in the boxer engine configurations, and V-shaped engines have both horizontal and vertical components of this reciprocating force, not just the vertical one like this one cylinder diagram we have right here. And lastly, we have the firing force. And so this firing force in this case will be up and down as well, just because of the combustion that's occurring in the cylinder shaft. But in V-shaped engines, these will be at an angle away from each other. So there are a number of factors that contribute to balancing these forces among the movements of the cylinders. So first of all, the number of cylinders is key to maintaining a balance between the reciprocating and rotational forces. So for example, in an engine with an odd number of cylinders will have an imbalance of these forces, whereas one with an even number of cylinders will have a balance. And so if we look at this one cylinder one piston engine right here, there is an imbalance of these forces because when the piston is at the top of its travel, the reciprocating forces are balanced, but when it's not at the top or the bottom of its travel and it's midway right here, then we see that the weight and the counterweight right here actually has a left-right imbalance in this force, and it causes a force that it goes side to side, which is an imbalanced force. And so this is why if there's an inline 5 or an inline 3, these engines will have an imbalance in these forces and have unnecessary vibration or noise. Now next, we have the angle of the V shape and the degree of rotation of the crankshaft between firings, and this is key in maintaining a balance of the firing forces, specifically in the V-shaped engines. So, there's actually a formula to calculate the optimal degree. So if you divide 720 degrees by the number of cylinders, you get a figure that represents the optimal degrees of the crankshaft rotation between cylinder firings, which is essentially what this equation is right here. So for example, this doesn't only pertain to V-shaped engines, it pertains to the flat 4 boxer engine as well. So for example, a flat 4 would fire at every 180 degrees of crankshaft rotation, because 720 divided by 4 is 180. And so having firing events that occur in equal increments is best for the balance. And so flat 4s fire at 180 degree intervals, and their V angle is 180 degrees, which is why the cylinders move along the horizontal axis. And this leads to a balance of the firing forces. And so this shows how all these different factors can contribute to balancing those 3 key forces that we talked about. And so now that we've established what the different cylinder, piston, and engine configurations are, and how each is key to maintaining that balance of those 3 key forces we talked about, we can analyze their impact on the engine as a whole, specifically the engine's power. So when we talk about power, we know that power is equal to work over time, and we also know that this work is equal to force times distance. Now when we talk about work done in an engine, this force is actually what is right here, and the force is located in the cylinder shaft, and that's due to the pressure that is occurring right there as a result of the ignition and combustion that's occurring in the cylinder shaft. And then the distance is the piston's movement in the cylinder shaft that is right here. And so we know from this that the power is directly related to solely to the movement of the pistons and cylinders in the engine. And so this is how we define the power of an engine. So knowing this, we can analyze how these different cylinder configurations can actually alter the power of the engine. So for instance, we have a V6 engine right here. We have a V8, and then we have a V12. The number is essentially representing the number of cylinders in the engine. And so we can see how there's a direct relationship between how adding the number of cylinders causes an increase in the power of the engine. This is because the work done is due to the motion of the cylinders, and so by adding more cylinders, we add and multiply the amount of work done being in that engine, but the time it takes for the piston to complete that cycle is still the same. And so the total work increases, but the time stays constant. And so this results in an overall net increase in the power of the engine. And so this is why we see that as you go from V6 to V8 to V12 and add the larger number of cylinders, there's actually an increase in the power of the engine, which is how these V12 sports cars have more power than maybe like a V6 normal sedan. And so that's essentially how these cylinder configurations and types of engines can have an incredible impact on the engine as a whole.